Good day and welcome to this discussion on Assignment 10. In the first question, we again deal with a continuous function that is defined on a closed and a bounded region. As you know, by Theorem 111, we do know that a continuous function that is defined on a closed and a bounded region will attain a global maximum and a global minimum. But that is not what's asked in this question. Given that that is the fact, you need to find the global maximum and the global minimum. We know that the local extremes will occur either at the critical points, that is where the gradient is zero, or the singular points, that is where the gradient doesn't exist, or on the boundary of the region. So let's begin by finding the gradient. For the gradient, we calculate the first order partial derivatives of f. As these derivatives exist everywhere, it is clear that there are no singular points. We need to find the points where the gradient is equal to 0, and that gives us these two equations labeled 1 and 2. It follows from the second equation that either y is 0 or x is 1. If we put y equals 0 in equation 1, we find that x is negative a half, and if we put x equals 1 into equation 1, we find that y is plus or minus the root of 3. We need to check that the given points are indeed in the set D. The test shows us that the points with coordinates 1, plus or minus root of 3 cannot lie in D. Thus, the point negative a half 0 is the only critical point of f in D. We now need to check the points on the boundary. Let C1 be the part of the boundary that lies on the x-axis. That is where y is equal to 0 and x lies between negative root of 2 and root of 2. By substituting y equals 0 into the formula for f, we find a function of one variable only, let's say g at x equals x squared plus x. Now you must remember that for a function of one variable on a closed interval, the extreme values are either at the critical points or at the endpoints of the interval. By calculating the first derivative and equating that to 0, we find that x equals negative a half is a critical point. Thus, the only points in the closed interval negative root of 2 to root of 2, where g possibly attains an extreme value, are at x equals negative root of 2, the one endpoint, or x equals negative a half, the critical point, or at x equals to the root of 2, the right endpoint. This means that the only points on C1 where f possibly attains an extreme value are at the points negative root of 2, 0, or negative a half, 0, or root of 2, 0. For the rest of the boundary, we consider the set C2, which consists of the points on the upper half of the circle. That means y equals the positive root of 2 minus x squared, with x again between negative root of 2 and root of 2. If we substitute y equals the positive root of 2 minus x squared into the formula for f, and we do a bit of simplification, we get a function of one variable, h at x equals x cubed minus x plus 2. Using the first derivative, we see that the only critical points of h are at x equals plus or minus 1 over the root of 3. Thus, the only points in the closed interval negative root of 2 to root of 2, where h possibly attains an extreme value, are at x equals negative root of 2, the left endpoint, or x equals minus 1 over the root of 3, one of the critical points, or x equals 1 over the root of 3, the other critical point, or at x equals root of 2, the right endpoint. We again need to check that these possible values that we have attained really lie within the region D. We note that if x is plus or minus 1 over the root of 3, then y is the root of 5 over the root of 3. Since the root of 5 divided by the root of 3 is clearly less than 2, we can be sure that these points will lie within the region D. So the only points on C2 where f possibly attains an extreme value are at the points negative root of 2, 0, negative 1 over the root of 3, the root of 5 over the root of 3, 1 over the root of 3, root of 5 over root of 3, and root of 2, 0. We have now found all of the points where f can possibly have an extreme value, namely the critical point, the points on C1, and the points on C2. What remains now is for us to calculate the function value at each of these points. Once we have calculated all the function values, we need to find the greatest of these. That gives us the global maximum of the function, and we need to find the smallest of these, which gives us a global minimum. In this case, we find that the global maximum of f is 2 plus the root of 2, and that occurs at the point root of 2, 0, and the global minimum is negative 1 over 4, which occurs at the point negative a half, 0. That concludes the discussion of problem number 1. In problem 2, we are instructed to use the method of Lagrange multipliers. You need to realize that there are always two parts in this method. You need to find some function that needs to be maximized or minimized, and you need to find a function that describes a constraint. So that's what we first need to do. We begin by assuming that the point A, B is the vertex of the ellipse in the first quadrant. This immediately means that A and B are positive. Also remember that the other vertices must also lie on the ellipse, so the lengths of the sides of the rectangle are 2 times A and 2 times B respectively. That allows us to give a formula for the area, namely capital A at A, B is 4 times AB. This gives us a function that we need to maximize. The constraint in this case is pretty obvious. We know that the point with coordinates A, B must lie on the ellipse. That means those values must satisfy the equation of the ellipse. So we must have a squared plus 4b squared equals 4, and therefore we can let g at A, B be equal to a squared plus 4b squared minus 4. That is our constraint. Before jumping into the method of Lagrange multipliers, we first now need to check that the conditions are met. The first condition is that the functions that we consider must be defined on an open set. Well, since A and G both have R2 as a domain, they are indeed defined on an open set. Secondly, by calculating all the partial derivatives of these functions, we can see that they have continuous first-order partial derivatives, since all of these are polynomials. Finally, we can see that the gradient of g is 0 if and only if both A and B are 0. Since the point 0, 0 is not on the ellipse, we have that the gradient is not 0 for all points on the ellipse. That now means that we can indeed use theorem 126. So we now define a new function L by letting L at A, B, lambda be f at A, B minus lambda times g at A, B, which means L at A, B, lambda is equal to 4ab minus lambda times in brackets a squared plus 4b squared minus 4. We then calculate the first partial derivatives of L, and the results are given there for you to check. To find the critical points of L, we look for points where the gradient of L is equal to the 0 vector. That gives us the three equations that are labeled 1, 2, and 3. We have already seen that the point 0, 0 is not on the ellipse, so we may assume for our calculations that A is not 0 and B is not 0. We can therefore multiply equation 1 by 4b and equation 2 by A. That gives us the equations labeled 4 and 5. It follows from equations 4 and 5 that A squared is equal to 4b squared. In other words, A is equal to 2b. Remember that both A and B are positive. If we put A equals 2b in equation 3, we find that B is a half, and so A is 1. Thus, the maximum area of the rectangle is A at 1, a half, which is equal to 2. That concludes the discussion of problem number 2 and also of assignment 10. Goodbye.